Right, hopefully you have already watched the video on introduction to wood, and today we want to talk about some of the things that we said would affect the wood properties. And the very first thing that we need to make sure we understand is how wood is coming out of the log, because that actually does affect the strength of the wood. So common cutting methods are shown here. The most common plain sawn, we literally just ripping right through the board horizontally or right through the log, the same thing you see with billet sawing. Now we see commercial quarter sawing in the bottom left, and then some other ways of describing quarter sawing on the bottom right, as well as radial or true rift sawing. And you can see with true quarter sawing and true radial or rift sawing, you have a lot of scrap lumber. Now there's a problem with the names listed here. What is known to the log cutter as rift and quarter sawn methods is different than what's going to be known as the person using the lumber for what is a quarter sawn or a rift sawn board. So this is great that we see basically how we cut out, but let's actually look at a different orientation to see what we actually call a plain sawn, a quarter sawn, or a rift sawn board. And I want to zoom in a little bit closer on our actual boards at the bottom, because this is what matters. Now this is a great image. This has come out of the Fine Home Building magazine. And what we see on our first board is the rings on the cut face, so the smaller area that we see on the very front, those rings are relatively parallel to the top face of the board and can have, according to Fine Home Building, up to a 30-degree angle from the top face of the board. Versus quarter sawn, if you look at the rings on the front edge of the board, you can see that they're almost perpendicular to the top face. Fine Home Building says they could be anywhere from perpendicular to 60 degrees. Other sources say they have to be between 80 and 90 degrees, like just darn near perpendicular. Between plain sawn and quarter sawn, you then have rift sawn. The perfect rift sawn board would see all of your rings at about 45 degrees from the top plane, but here they say they could range between 30 and 60. Now your textbook has a similar photo, and you'll see in your textbook that it actually mentions you could be anywhere for flat sawn up to 45 degrees from parallel to that top flat face. Rift sawn 80 to 90. I'm sorry, quarter sawn 80 to 90 and rift sawn 45 to 80 degrees. It's not as much of a concern of whether you know these angles and these degrees, but rather that you could look at the edge of a board and estimate this is flat sawn, this is rift sawn, this is quarter sawn. Or even more importantly, as you look at the face of a board, can you say that the grains are tangential to a side or radial to a side? And so what do we mean by that? Well, let's look at how we typically might look at a trunk of a tree. So the trunk, the long axis is our longitudinal direction. Our pith, we can see there, is on the right, bark out on the left. And so the rings, a tangential direction to the rings is shown. In fact, let's zoom in and see that a little closer. So here's what we would consider tangential to the rings versus radial would be heading in towards the pith or perpendicular to the rings. And so in a plain sawn board, tangential rings to the face. In a quarter sawn board, we're more radial to that wider face. Now, why does this matter? Well, let's talk about shrinkage. Shrinkage is defined with respect to the rings and whether or not we're tangential or radial. And in fact, here's a common chart that would tell us how much moisture or shrinkage to expect with respect to moisture content. And we can see that we expect more shrinkage along tangential. As we reduce the moisture content, we would expect more shrinkage to tangential than we would radial, and hardly any longitudinal. But it's interesting because we can see that we have zero expected shrinkage when we're at this fiber saturation point. And of course, let's remind ourselves that tangential, that's where we're seeing the most shrinkage. So this fiber saturation point is pretty important to define because that's where we start shrinking. So let's look at an image, and this is a cartoon image of those same scanning electron microscope images of the cells in the tree that we saw in video 1. And so the first thing we see are those large open cavities, and those are the cavities of the tracheids. Now, The water in those tracheids that's inside the cavity of the cell, that's known as free water. And the water that's actually trapped in the wall, so all those smaller circles of water is just indicating water that's inside of the fiber walls of the tracheids, that's our bound water. So the wood, when wood dries, all the free water will evaporate before any bound water leaves. Once the free water is all gone, then the bound water can start to evaporate from the saturated cell walls, and that's important. Now that moisture content where 100% of the bound water is still there, but all of the free water has evaporated, that's known as your fiber saturation point. You have just enough water to saturate all of the fibers, all of the cell walls, but no extra water in your cavity, right? Now, if you're in design of wood and looking at shrinkage or different measurements based on the fiber saturation point, that's typically assumed to be at about 25 to 30% moisture content. Now, some key things happen. In situ, for a tree that's just living in the wilderness, your moisture contents should range, should be at least 30%, because you don't want a tree that is so dry it doesn't have its cell walls saturated. But it could be up to 200%. If you have very large pores, very large tracheids, and you have a lot of water in your tree, you could have as much as 200% moisture content, which is crazy, more water than wood by weight. Now in construction, you actually need a much lower moisture content, say 7 to 14%, depending on your part of the country and how much humidity plays a part in your wood. And so that's what you want in the wood that's in your walls. And so to get that, you need to season your lumber or kiln dry it. And so by definition, if you have a moisture content less than 19%, you have seasoned lumber. If your lumber is not seasoned, it's called green lumber. Not by color, it's just wet. And if you go to Home Depot or Lowe's, they sell both kiln dried and green lumber. The green lumber is cheaper, so people will buy it, but I have walked out with a piece of green lumber on my shoulder, and by the time I got to the truck to throw it in the back, I had a wet shoulder. It had that much moisture still in it. And so as it would dry, it's going to warp. It's not, it's harder to build with. Kiln dried and seasoned lumber is definitely better quality, and I need that green lumber to dry before I were to say wrap up a house, because then I could have moisture issues, rot, mold, etc. All right, now the FSP is important when we talk about strength and size or expected size of the lumber. So free water, any water that's just trapped in those cells, it doesn't have any effect on lumber size or strength, but when we start reducing the bound water, so we've evaporated out all the free and then we start reducing the bound, we actually start to see the strength increasing and the shrinkage increasing as the moisture content is decreasing. So less water means a smaller size and more strength. Conversely, if we have, say, a seasoned board and so we have a low moisture content and we start adding moisture, adding bound water up to the FSP, we would actually see a decrease in strength and we'd see our boards begin to swell. And of course, the amount of strength change or swelling or shrinkage would be affected by the species of the wood. Well, the orientation of the grains also affects strength. So let's remind ourselves, so here's our plain sawn, which is the most common for commercial construction lumber way of cutting the boards. And we can see the growth rings which create the grains. On the side here, we can see that it's talking about they're not straight. They're not going to be parallel to loading like our loading diagram we see here when we see the direction of the stresses. Furthermore, on the top face, we can see that because we have face grain, we have very irregular shapes, and so we're definitely going to have places where we're perpendicular and not parallel to grain. And so that can reduce the strength of our board. Well, Hankinson fortunately gave us this great formula here where we can say, all right, sigma P, which is the strength perpendicular to the grains, and sigma Q, strength parallel to the grains. Whoops, I have that backwards. P is parallel and Q is perpendicular. If we multiply those by the angle by which we are off, being having our grains run parallel to the edge cut of the board, we could actually figure out what the reduction in stress is But that sounds really hard. And what are you going to do? Look at each board individually? I mean, that's just crazy. Well, fortunately, we never have to do this formula as a practicing engineer because it's done for us at the manufacturers when they're actually grading the lumber before it leaves the mill. And they're looking at how off of parallel to the edge of the board the grades are, and then they would reduce the grain grade quality. And a lower quality grade gives you a lower allowable stress. Whew, so that's useful to us. We don't have to do this. Another thing that also affects, and we mentioned in our first video, that affects how much allowable stress we can put on the board is our load duration. In fact, with timber, you have to multiply whatever the grade's allowable stress is by a lot of factors. Some of it is how much moisture. Is it going to be exposed to moisture? Boom, reduce the capacity. Do you have a lot of boards? A repetitive use member. We see redundancy is great. You can actually increase your strength. Well, this plot is how long is your load there? What if it's a short 10-minute load, like from a heavy wind or an earthquake? You can actually increase your load by 60% or multiply by 1.6. What if it's a 2-month load, like a snow load? You can have a slight increase in your strength. But what if it's an everyday load, a permanent load that I've marked here with the green line? That almost brings your strength down, according to this chart, by about 0.92 or 92%. And in fact, what code requires is if you have a permanent load that's always going to be on that beam, weight of a wall, weight of floor beams coming in, then that actually has to reduce the capacity, allowable capacity, by 10%, or you're only allowed a factor of 0.9 of that. You're allowed 90% of the capacity. And just quickly to look at some of these capacities and how it is affected by the grade, here is a cool table that comes out of the actual NDS, the National Design Specifications for Wood. Now, your textbook has a sample of this table. It doesn't say it's the NDS, but it gives you, for a particular species of wood, the allowable stresses based on the species or the grading that was given to that particular species. It's not complete, but here's a sample. This is kind of big, so let's zoom in on Douglas fir larch, a super common wood here in the Northern California building trades. And we can actually see that if we have select structural, the top grade, we're going to get an allowable bending stress that we can start with before multiplying it by factors of 1500 psi. Dropping down to just number 1, that drops to 1000 psi. So we can see that's a big jump of 50%. When we get to our stud and construction grade, those are also quite low. And in utility, never get a utility board. Number 2 is typically what you'd want to build with, except for maybe wall studs could be stud or construction grade. When you're talking about larger beams, you're typically specifying number 1 or better. You also should notice, just out of interest, you're getting allowable stresses for a lot of different loading cases. So you could have bending, tension parallel to grain, shear parallel to grain, compression parallel to grain. But the only thing they're giving us perpendicular to grain is compression, because as noted in the first video, we don't load wood in tension perpendicular to grain. All right, so these are some of the factors that will affect the strength of wood. Defects were also something we said could affect strength, and that's coming later in the lessons. Thanks for watching.